Hello everyone, and welcome to Sky Scholar, the channel where you can learn about new concepts in physics and astronomy. I'm your host, Dr. Robitaille. Today I want to continue presenting some of the most easily visualized proofs that the photosphere has a real surface. If you want to learn more about some of these proofs, you should look at this paper, which is also linked below. Remember that in the standard model of the Sun, we are told that the solar surface is nothing but an optical illusion. Solar physicists discard that the photosphere has a true surface because gaseous plasmas are devoid of any surface by definition. Now I'd like to speak to you about some of the proofs that the Sun has a real surface. Astronomers have imaged the solar surface in great detail thanks to the resolution of the 1-meter Swedish solar telescope. When analyzing the resulting images, scientists describe the photosphere as filled with structural features resembling canyons, mountains, and gorges. Just have a look at a few of these pictures from the 1-meter solar telescope. Wow! Now examine this video of a sunspot and nearby granules. Whether we are looking at sunspots or other structures, we should no longer discount the importance of what can easily be seen with our own instruments. It is clearly not reasonable to account for all these optical changes with opacity arguments. We can even see solar tornadoes on the Sun. These objects very much resemble tornadoes on our own planet. Tornadoes on Earth are atmospheric instabilities produced when two very different air masses in terms of temperature and moisture are fueled by wind shear. This wind shear is the result of interaction with the Earth's surface compared to upper elevations. The wind closest to the ground has decreased velocity relative to that in the upper atmosphere. Once again, the fact that the Earth has a surface is inherently tied to tornado formation because real surfaces are always involved in the generation of shear forces. As a result, a true surface on the Sun helps to account for the presence of solar tornadic activity, much like the surface of the Earth provides a basis for generating shear winds and atmospheric instability. Let's now talk about the Sun's radius. We know that the Sun has a stable radius, and this radius has been measured at 696,342 plus or minus 65 kilometers. The error in this measurement is on the order of 1 part in 10,000. That is outstanding precision when you consider that in a machine shop, a standard dial caliper is precise to only 1/1000th of an inch. We know that the solar surface is not smooth, so this measurement is just remarkable. This is something which is not possible if the solar surface was truly a gas. Gases do not have easily characterized dimensions, and their boundaries are always ill-defined, unless they are enclosed. In the end, science is evidence-based. Where is the evidence that the solar surface is but an optical illusion? Instead of fitting theory to evidence, scientists are now discarding the evidence in order to maintain their theories. Solar physicists should not be able to argue that a gaseous plasma might change its opacity in order to create the illusion of a real surface when it is evident that a real surface exists. It is much more reasonable to say that the surface is well defined and composed of condensed matter. Then we have the fact that the Sun is oblate. It is not quite spherical. This isn't just in our Sun either. The oblateness of certain stars, such as Regulus, Altair, and Achernar, can be particularly severe, and this is direct evidence that these objects are comprised of condensed matter. Why? Let's talk about what causes oblateness. As an object is rotating about its surface, the material at the equator is able to physically pull towards itself the material at the poles. This requires internal cohesive forces which gases do not possess. A gaseous star can never be oblate as a result. Solar physicists must currently invoke externally directed pressure at the equator or the effect of magnetic fields in order to account for the behavior of stars. But we have already learned that gas pressure requires a true surface, and the known magnetic fields of the Sun are much too chaotic in nature to be part of supporting surface structure when the same type of field is applied to the stars. In fact, the observation that stars can be oblate and eventually, if this gets too severe, break up into two separate objects was one of the arguments which James Jeans used. He highlighted that the stars were liquids and condensed matter in the early 20th century. Jeans came to this conclusion by noting the tremendous number of binary stars in the universe. Let's look at another object to illustrate the point: the Earth. Our planet is also oblate. It has an equatorial radius of 6,378.1 kilometers versus a polar radius of 6,356.8 kilometers. The Earth is oblate because it is a rotating object of condensed matter with internal cohesive forces pulling material towards the equator. Gas pressure is not involved, and neither are magnetic fields. Once again, remember Newton. To the same problem, ascribe the same cause. The sun and the stars are oblate, and they are telling us that they are composed of condensed matter. Related to the sun's appearance, helioseismic studies have also revealed that it displays higher order shape. The sun has quadrupolar and hexadecapolar shape terms, which depend on solar cycle. Once again, it is impossible for a gaseous object to sustain such terms, as gases don't have internal cohesive forces. The next proof relates to the well-known rotation of the sun. This rotation was first discovered in 1863 by Carrington using sunspots. Carrington was an amateur astronomer, and his life was chaotic to say the least. If you wish to learn more about some fascinating aspect of this man, have a look at this book about early astronomy. It is a great read. Eventually, it was discovered that the solar surface rotates faster at the equator, and this rotation decreases towards the poles. This is commonly referred to as differential rotation of the sun. It takes only 25 days or so for the equator of the sun to complete one rotation. But if you move up about 30 degrees, it takes about 27 days. As you move further up, it can take even more time, with an average of 35 days at the poles. The movement of matter which is associated with differential rotation is tangential to the solar surface. Differential rotation is often used by scientists as evidence that the sun is a gaseous plasma. But in fact, differential rotation only provides evidence that the photosphere is fluid. It can be a gaseous plasma or a liquid, and either can account for differential rotation. In order to select the proper conclusion, it is important to note that the sun contains flows which are perpendicular to the solar surface. We see this in the solar winds, for instance, above coronal holes. Here is a video clip of a coronal hole. When these holes are viewed from the Earth, we know that they are the source of powerful solar winds perpendicular to the solar surface and directed towards our planet. In addition, the sun has plasma jets which can protrude perpendicular to the solar surface and inject matter into the corona. These examples show that the solar surface of the sun exhibits material flows which are orthogonal to one another. This is just like the atmosphere of the Earth. Most of the atmosphere of the Earth is gaseous. The atmosphere can possess strong upward currents, while the oceans below simultaneously display horizontal currents. Both are permitted because the oceans have a real surface. In a similar way, the sun is able to sustain orthogonal flows at the photosphere, and these imply a phase transition at this level. The surface of the sun is made of condensed matter, and the outer atmosphere of the sun is comprised primarily of gaseous plasma. In closing, I hope that you liked this short video relative to the true surface of the sun, and will join me as we look more closely at the sun, the stars, and beyond. If you enjoyed this video, please leave a like. In addition, subscribe if you want to journey with me through space here at Sky Scholar. Comments are always welcome down below. I'll see you soon on our next video.